Hey everybody, and welcome to the top of Manastash Ridge, where we have 3 rock layers exposed in a ridge above Ellensburg, Washington. I'm your Geology 101 lab instructor, Ned Zentner, and I'm happy that you're with us today. Students, this is only 20 minutes south of Ellensburg. If you've got a car, come on up here. This is a beautiful spot. There's a viewpoint close to the top of Manastash Ridge as you head south on Interstate 82, heading toward Yakima. Blue sign saying viewpoint. This is it. And instead of staying in the parking lot and doing whatever, throwing garbage out the window, maybe you can actually come over here and look at this wonderful geology that's exposed above the parking lot. It's a spot we've used for 30 years and will continue to use. It's a very handy place to learn the geology of Central Washington. Let's get started. Okay, well, the first thing we want to do is just make some simple observations. Observation number 1, there's a truck that's decided to come through here. I think we'll let it roll. We'll get over the guardrail, give this guy a little bit of extra room. This is a place that's about 1,000 feet higher than Ellensburg, and so the trucks have to come up this grade. And so not only is there a great view across the Kittitas Valley over to the Stewart Range, pretty hazy this morning, so I'm not going to bother, but I think anybody who has an interest in Central Washington geology might want to come up here and take a look at these rocks, which we're going to do right here. Now, this is Geology 101 Lab, so let's be very basic here to begin. We always, with these field trips, separate observation from interpretation. We just want to be disciplined about this and just look at the layers first of all, carefully collect some facts, observations, thinking like a second grader would be the best, and then we can go ahead from there. So there are 3 rock layers here. I don't know if you can see them. There's an obvious white or kind of tan, light tan layer. There's a brown layer up above, and there's maybe you can see a brown layer down below. Let me help you. So here's a sketch in the lab manual that shows our 3 rock layers, 1, 2, and 3. And a key concept that's not going to be a huge part of today, but these 3 rock layers used to be flat. They used to be horizontal, layers 1, 2, and 3. And layer 1 is the oldest and layer 3 is the youngest. And these layers were created 15 million years ago. Since that time, the layers have been slowly tilted to about a 30-degree angle away from horizontal. We don't really care about the tilting. We don't care about the truck who's going to come through right here. He wants to get on camera. Who can blame him? But instead, we want to realize that this is a story about these layers being created long ago. This episode of Nick from Home, Nick on the Fly, brought to you by GEOL Fruit Company. GEOL apples. You gotta love them, from Yakima, Washington. Okay, so we have our 3 layers. Now we want to be disciplined and realize that not all 3 layers are the same. So I suppose we ought to grab a rock hammer and see if we can figure out what kind of layers those are. And lab students, I'm going to give one thing away right now. Here is the data chart that you're going to be filling out, and maybe are filling out right now as you watch this video. Layer 1 is a basalt lava flow. Layer 3 is a basalt lava flow. We don't know yet what layer 2 is. We're going to do that in a second. We're going to describe the texture of each of these layers. And I just gave you a number. You might have to rewind to catch it again. The number of degrees that these layers have been tilted away from horizontal. So this page 35 is where we're collecting our data for this Geology 101 lab. All right. Hammer. Camera in the left hand. Let's see how this works. I think we'll just do a quick 1, 2, 3 without breaking anything open first. Let's just kind of give you a shot. Again, we're just thinking as a beginning student. So here's layer 1. And what do you notice? I changed my mind. We'll break some of this open. So can you see that much of this layer 1 has a bunch of tiny holes in it? Tiny little holes. And what did I say layer 1 was? What kind of rock? Basalt, right. Do you know anything about basalt? Basalt is the kind of rock that forms in Hawaii. And this place used to look like Hawaii 15 million years ago. I'm trying to get out of my own shadow here. Let's bust a little bit of this. Come on, baby. Thank you. Okay. So depending on the quality of the focus here, I'm hoping you can see that there are some little sparkles, some little fresh minerals that we can see. So there's fresh sparkly minerals that reflect light, plus there's a bunch of holes. I can't tell how well the focus is doing here. Okay? This is an aphanitic texture, meaning that there are no minerals visible in this basalt lava flow. We can see random sparkly minerals, but the texture of this igneous rock is aphanitic. A-P-H-A-N-I-T-I-C, aphanitic. Now, let's skip over layer 2 for a second. Let's go right over to layer 3, which is younger. And there's a bunch of reasons we know it's younger. Let's just go ahead and just say that. The higher you go in a layer cake, the younger the layers are. What's with all this garbage these days? What is going on with the garbage? Are you a garbage person? Jeez. Editorial comment. Now I'm not gonna play with these rocks down low because I don't know from what layer they fell. Terrible grammar there, but you get my idea. I got to get up here to bedrock that's in place. So this is part of layer 3 that has not been, that has not fallen off of the hill yet. But we're going to encourage a couple of these guys to come down the hill. Okay, layer 3, according to your chart, we know this is a basalt also, but is this possibly the same basalt lava flow, or is this a different one? To confirm that it's different, let's get a piece of this stuff open. Thank you. Oh, perfect. So I'm hoping here that what do you notice that's different? It's a basalt. It has sparkly fresh minerals, but is this an aphanitic texture? The answer is no. Aphanitic means 100% microscopic invisible minerals, and I hope that you can see that there's at least one, and here's a second one here, visible mineral. Why isn't the focus cooperating here this morning? I don't get it. Let me focus on my hand. Maybe that will help. Okay, so this is a porphyritic texture. This is a different lava flow with a different texture. The texture here is porphyritic, meaning we can see visible and invisible minerals in the same lava. And these are plagioclase feldspar minerals. So you're like, hold on, how do you spell porphyritic? P-O-R-P-H-Y-R-I-T-I-C. And this is a visible plagioclase feldspar mineral surrounded by a bunch of tiny stuff. Okay, so layer 3 is a basalt lava that's younger than layer 1, but it's definitely a different lava flow because of the different texture. Okay, let's get down off the hill without falling. Okay, let's back away for a second. I don't think I'm going to edit much of this at all. You're just going to have to roll with me freeform here. Okay, so what have we done so far? We've looked up close and personal at the two basalt lava flows here that are exposed in this. This is an artificial road cut, by the way. They put this viewpoint in 50 years ago when they built this freeway, and they did us a favor. So layer 3 basalt, layer 1 basalt, aphanitic texture number 1, porphyritic texture number 3. These are two different basalt lava flows that flowed out of fissures over by Idaho, and those lavas flowed west. So these lavas, when they were molten, are flowing away from you. You're looking west right now. And roughly 15 million years old. This is part of the Columbia River basalt lavas, or the plateau lavas, or the German chocolate cake. These are two of the layers in the German chocolate cake. And again, we can go to the next ridge to the north, over to the Wenatchee Mountains. We can go to ridges to the south and find the next basaltic ridge, and we'd find some of these same basalt layers exposed, and some different basalt layers exposed. Okay, you with me so far? I hope you noticed that there weren't any vesicles in layer 3, but there were a bunch of vesicles in layer 1. We're still just doing observation now. Now, obviously, the star of the show is layer 2. That's what you really want to look at, isn't it? And I don't know. We really don't know what kind of rock this is, and before we need to decide what kind of rock it is before we come up with the story. But whatever we come up with, let me back away for a second, whatever we come up with is a story of what happened here in central Washington 15 million years ago. And for beginning geology students, you go, okay, well, I guess this all happened up here on top of this ridge. You know, you're trying to use the modern topography, in other words, where the hills and valleys are, to factor into your story. And my job here is to get you to say, this is a story that happened before everything that you see. Before these ridges, before the valley that Ellensburg sits in, before it became dry and desert-like here. This is a story when these areas were flat, before they got tilted, and therefore this is a story about when this place used to be hot and humid. And there's a whole nother discussion of why we know the climate was different then. Okay, so with that general context, let's go over and get our nose on the outcrop here. I don't know, can you see Mount Stewart in the distance? I feel like it's so hazy, but I still feel like I have to zoom in a little bit for you. Maybe you can't. Beautiful Stewart Range on the horizon. Much, much older story than what we're doing here today. Okay, let's pick up the pace, he says to himself. Okay, well, we're a beginning student. We don't really know what we're looking at. What can we observe? Well, it's light tan or white. Okay. What else can we observe? Well, there's some layers here, isn't there? There's some interesting, amazing kind of horizontal layers-ish. But then if we go back out for a second, can you see that there's a second set of layers that are like this? So there's kind of layers like this, and then there's also a bunch of horizontal layers. So two sets of layers within this layer 2, whatever it is. I'm holding off on giving it a name because you don't know what the name is yet. Now notice that there's a bunch of loose, looks like sand down here below, and obviously, I hope it's obvious to you, this sand eroded off of this layer 2. So let's at least just take a glance at this stuff. okay. I mean, it's kind of like sand at the beach. You're like, okay, is this sandstone then? Well, it might be, but we're not sure. Let's go to the horse's mouth. Let's go right to the actual stuff that hasn't crumbled away yet and look a little bit more carefully. To be totally by the book here, we want to make sure we're studying something that is in this layer. So I'm going to kind of come in with the pointy end here. Try to get a little block for us. Oh yeah, there's a block. There's a block. Come on up. Let's get some light on this surface for the first time in 15 million years. Oh yeah. All right, how are we doing on focus? So this doesn't look like lava, does it? It looks like it's made out of individual particles. In fact, I can do this. That's how strong I am, ladies and gentlemen. I'm not that strong. I can take this white layer 2 and I can bust it in my hands, and I can make these grains of sand fall out of this layer 2 without a whole lot of effort. So these sand grains have been glued together for 15 million years until this morning. Okay? All right. So let's drill down a little bit finer here. Let's bust a little bit of this. Hello. Come on. Good. Good. Okay, I'm hoping that you can see. You know what I think I want to do now? I want to come down and get a bunch of this sand in my hand. Let me have a seat. If I have a seat, maybe I won't get up again, but oh, yeah. So can you see, especially if I get this sand down to a very fine layer within my palm, I'm hoping to show you that not all of the sand is the same color. How's the light? Is that working for you? Maybe if I just do this. You know, if you go to the beach, depending on what beach you're on, oftentimes the sand is identical. Each grain of sand is the same color. And I would say that this sand is pretty well sorted. In other words, most of the sand grains are about the same size. But I'm really hoping that you can see with the light here that we have some black sand, some gray sand, some white sand. And if you can't see that, you're going to have to take my word for it, because that's what I can see here. Okay? A variety of sand. So this is called an Arcosic sandstone. A-R-K-O, Arcosic. A-R-K-O-S-I-C? I guess so. Arcosic. And that's important because Arcosic sandstones are dirty sandstones, meaning that there is a variety of sand inside of the sandstone. This is a sedimentary rock called a sandstone, but it's not a quartz sandstone, which has 100% quartz grains, and every grain is the same look. This is an Arcosic sandstone, meaning that we have a variety of sand. We have some quartz sand, some feldspar sand, some biotite, some hornblende in this stuff. And it's layered with these crazy layers. Now, I'll do one more observation and then we'll cut to the fun part, which is telling a story. How's your vision here, especially as we go up this hill? I'm barefoot right now. There's nice. It's like walking on the beach. I'm walking on the beach on a top of a ridge in central Washington. 2,500 feet elevation. I want you to keep an eye on this layer right here. We're going to go up a little higher here. You see how regular and consistent this ledge? Oh, there's going to be a good shot right up here. I've been walking up this little gangplank here with students for 30 years now, once a quarter, and this is an unlimited supply of little pebbles. That's what I'm hoping to show you. Can you see this? In other words, within this sandstone, which is mostly that sand grain material, if we zoom in here and get out of my own shadow, these aren't grains of sand. These are little jelly beans. These are little pebbles. I don't like this. I want to get a little higher so you can get out of there. You don't have the shadow to work with. Yeah, oh, this is good. This is good. Good, 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 good. So within this rather thick sandstone, which is mostly the same size sand grains, there's this one very clear ledge of pebbles, and it's a consistent layer of pebbles. In other words, it goes all the way through this sandstone. It's not just stuff that's been glued onto the surface here. And what do you observe? They're rounded. They're about the size of jelly beans. Again, I've been pulling these jelly beans out of this sandstone for 30 years, and there's more. It's not a finite resource. There's millions more inside of the hill. Okay, well the question is there a story with this layer? Oh, I can't get this one out. What? Why? Oh man, I'm going all lefty with my rock hammer. No big deal. There we go. That's a cute little guy. Beautiful little quartzite. Yeah, nice. There's one other observation we can make, and maybe you noticed from down low, but do you see that there are some amazing circular, almost basketball-like features in the bottom of layer 3, which we know is a basalt lava flow? Let me get up here for a second. Yeah, the light is really good now to see this boundary between the top of layer 2 and the bottom of layer 3. These are pillow lavas. Basketball sized and shaped brown things surrounded by kind of orangish, greenish, grayish stuff. And you might even notice that the top of layer 2 is discolored to kind of a green color. So we need to deal with these pillows as well. And the pillows are telling us something about what happened here long ago. Okay, so what do we know from our observations? Layer 1 is basalt. It's aphanitic with vesicles or little gas bubbles at the top. Layer 2 is an Arcosic sandstone that also used to be flat and has been inclined, made out of sand grains for the most part, but at least one very clear layer of jelly beans or tiny rounded pebbles. And layer 3, which we can only see the base of, in other words, this layer 3 used to be 100 feet thick. So most of layer 3 is gone, but the very bottom of layer 3 is still with us. And this entire portion of layer 3 that we can see is porphyritic in texture, no vesicles, And there's pillows at the base. I feel like I should zoom in on the pillows for you from this vantage point. God, those are nice. That light is doing us great favors now. Let me just try to, try to just kind of slowly pan up. Slowly pan, Gizmo. Thank you. Pretty good. Oh, pretty good. All the way up. Okay? So what can we do storytelling-wise from this exposure now that we have our observations? The first storytelling is why the layers are no longer flat, why the layers are tilted. So Manastash Ridge is right in here. In fact, we can have this be Manastash Ridge. Why not? Let's have Manastash Ridge here. So we're going to make Manastash Ridge in central Washington. Isn't that cute? Let's do that from the side. Up it goes, making Manastash Ridge. And if we take Manastash Ridge and we form Manastash Ridge, you can see how the originally flat layers are going to get folded or tilted away from the crest of the ridge. And there's more than one of these, of course. There's dozens of these all through central Washington. The reason for the folding is the purpose of this board, and many of the regular viewers of this channel have seen this multiple times. But we now know, using geodetic instruments, GPS receivers that are permanently installed all through this colored area, we know that Northern California is a block that's pushing into Western Oregon, which is a block that's pushing into Western Washington. And we also know that Canada is not doing this rotation game. The Canadian Coast Mountains buttress. Thank you, Bob Butler, University of Portland. And so because of this ongoing rotation of these blocks, we continue to squeeze central Washington, making these folds and faults that you can see. So why did these layers, 1, 2, and 3, go from flat to inclined? The answer, hopefully you can see now, is because of this very regional story involving, come on Gizmo, involving this rotation story. Okay, that's the big picture view, but if we go before this rotation, in other words, when these lavas were being created, we didn't have the rotation like we do now. So let's go prior to the rotation, prior to the ridge being formed, and let's try to answer some questions about the creation of these 3 rock layers once upon a time. You still with me? Hope so. Okay. So this is, I'll do this kind of quickly, I think. This is our interpretations page, page 36. And again, if you're a great student, I want you to pause right now and just do your best to answer these questions. And I'll give you all sorts of leeway on what you write because I know you're a beginning student, but I would hope that you can kind of just use some logic and some reason to come up with a story for what these layers are telling us. But for the rest of the folks who are watching this, who want some answers, or for the crappy students at CWU who just want to copy down what I say, here we go. They're deposited horizontally, blah, blah, blah. We know that. What caused the tilting of the layers? I just talked about that. Why are there vesicles? In other words, those little bubbles, those little air holes, only in the upper zone of layer 1. So I showed you some of the vesicles, which are the little gas bubbles, only at the top. And if we took the time to go all the way down towards the middle and even the bottom of layer 1, we'll lose the vesicles. So do you have an answer for that? Why are there only vesicles at the top? The answer, if I was a prop person this morning, I would have brought a big stein of beer. If we pour beer into the stein and watch this beautiful head form on this beer, there's all these bubbles, aren't there? These bubbles are rising to the top of that stein of beer, or Coca-Cola if you swing that way. Same idea here. When this basalt lava flowed in horizontally, it was molten, there was dissolved gases in it, and as the lava was sitting here, layer 1 I'm talking about, nice and flat, as it was sitting here cooling, The bubbles were rising to the top and escaping out of the top of layer 1, the basalt lava flow, layer 1. But some of these guys didn't make it. And that's why we have these vesicles only at the top of layer 1. Make sense? Onward. The B lines in rock layer 2 are horizontal today, but not 15 million years ago. Were these layers dipping north or south when this rock layer was created? Imagine dripping water on the dipping lines. Water runs which direction? Who the hell wrote that question? What I'm calling lowercase b lines are these horizontal stripes or miniature layers within the Arcosic sandstone. And can you see them here in the flesh? Often students come up here and think, well, this is a windy place. This is probably just wind kind of whipping around this corner, making these B lines. But that's not true. This sandstone has been eroding for millions of years, and certainly has been eroding for the last 30 years, and these layers continue. So they are clearly within, not just on the surface, but within layer 2. So my question is, those B lines are horizontal today, but were they horizontal 15 million years ago? And the answer is no. It's kind of a weird coincidence. Remember, our layers look like this today, but remember what these layers look like when they were created? Right. So you're looking west, and north is to your right, to the Stewarts. So if we take our B lines looking west and rotate to the original position of the 3 layers, including the original position of the B lines are dipping which direction? And the answer is south. I hope you can see that. And as the clue I gave in the question was, if you drip water on these little guys, the water's going to run to the south. These are cross beds within the sandstone. Cross beds, those are the B lines, cross beds dipping to the south, which tells us that there was some sort of current, some sort of flow going north to south. This is the biggest point of today's message, today's lab. You ready? Because we have cross beds that are dipping to the south, that means something was flowing from north to south 15 million years ago when this sandstone was created. Let me back away for dramatic effect. Something was flowing north to south, laying down sand, and the sand was being deposited on these slopes that were sitting like this, dipping to the south. So the biggest question here is, what would cause that? Let me flip you around. So what would cause sand to deposit on a slope like this? Can you think of going on a vacation? Where is it sandy? The beach. Okay, that's water. Where else is it sandy? Worldwide, where's there a lot of sand? The desert. Or have you been to a sandbar in a river? So which of these are we talking about here? Does this sandstone represent a desert or a river? It doesn't represent a beach, because a beach is just kind of an oscillating thing back and forth. These are clearly cross beds flowing from north to south 15 million years ago, and our two choices are, does this sand represent an old river that was flowing to the south, or an old desert where the wind was flowing north to south? Those are our choices. What do you think? I'll wait. Okay, I'm done waiting. You got an answer? Do you like a river or do you like a desert? I think either is possible here. And you're like, whoa, 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 I want an answer. I got to turn this in. What's the answer? And this is a lesson in how we operate out here in geology. We all collect the same data. We all agree that the same data exists between all of us. We're all looking at the same facts. But it's healthy to entertain multiple explanations. It's healthy to do that, to keep your mind open to as many possible hypotheses as possible. And until you can find the data that eliminates a certain choice, we're going to keep these multiple ideas in the hopper. And right here at this particular spot, we have cross-bedded sand where the current was flowing north to south, and both are possible, except, let me flip you around. Except, do you remember what we have at the top of layer 2 and at the bottom of layer 3? On our sketch, it features lowercase c. So A are vesicles, B are the cross beds, and C are these pillow structures. The pillow structures tell us something very specific. And let's read a definition of what pillow structures are. Pillow structures. A structure in certain extrusive igneous rocks characterized by discontinuous pillow-shaped masses, a product of subaqueous extrusion. What? How's that supposed to help? Well, if you really break down each of those words and you think about it, the message is the only reason we have pillows here at the bottom of layer 3 is because there was water present late in the game. In other words, let me zoom you out. In other words, when layer 3 came in to this area and it was flowing from behind this way, remember these layers were flat, right? There was water here late in the stages of the sandstone formation, and we know that because of these pillows. We wouldn't have pillows forming in the bottom of this layer 3 if this lava was flowing over a desert. It was flowing into water. And we know that because lava splits into these fingers of lava, much like the pillows in Hawaii. Now, I was up there giving you a close shot. I'll come over here and give you a few more shots of this pillow. So if you want the desert to be a major player here for our sandstone, I'm fine with that, except we better bring in some water. We better bring in a lake or something to explain these amazing circular. You see them? Do I see them? Yes. Circle, circle, circle. You see them? They're just sitting on top of each other. And the loose, crumbly, orangish, greenish junk around the outside is called palagonite, which was originally obsidian, kind of a glassy lava that is unstable, so it breaks down, it devitrifies. So, we're teasing out a bunch of detail now, aren't we? We're looking at either a river system or a desert system with big sand dunes to explain this cross-bedded Arcosic sandstone. But you heard my major point here. We need water late in the game to explain these pillows at the bottom of layer 3. This is fun. And while we're going with it, so then how do you explain our pebbles, our jelly beans? I'm skipping ahead to the bottom question on the sheet. Here, I don't have to climb this time. I can come right down here. See these guys? come on. Come on, do I really need a hammer? No, right there. Okay. So it's almost continuous sand from bottom to top, except for this one layer of tiny pebbles, these jelly beans. What is your explanation? The only concept we really want is that if we have grains of sediment that are bigger than grains of sand, and that's what we do with that one layer of pebbles, we need higher energy. We need some sort of short-lived, high-energy event, either in the desert or in the river. Some kind of storm, some kind of very quick batch of high-energy rounded pebbles are going to be coming in and being kind of blanketed over that surface, and then it's over. And then we're right back to the business of making sand grains again. So the one ledge and continuous layer of jelly beans records a very short, high energy event compared to the medium to low energy of the accumulation of the rest of the sand grains coming from a source probably to the northeast of here. There's a lot you can get out of a place like this, isn't there? That's pretty much it. Well, that's probably enough for today. Thank you for joining us, everybody. Hope you learned a few things about Central Washington geology and also how to operate as a beginning geology student on one of these field trips. Basalt, Arcosic sandstone, then basalt, and the Arcosic sandstone with some very specific clues to what this place was like long before the ridges grew 15 million years ago. Nick on the fly, Ned on the fly. I love you, over and out, goodbye. Thanks for watching.